Now that we know how to conduct tests for population proportions, that was section 10.2, and population means, which is 10.3, we have to do the same thing but for population variance and standard deviation. Now I say the same thing, but this test actually has some significant differences. I mean, it's still a 6-step process, but there are a few things that are quite a bit different from the other tests. For starters, it only has 2 requirements. It has to have a random sample and it has to have normal. You lose the independent factor, that's not really mentioned in here. And then also you lose this part, right? That n is greater than 30, or from section 10.2, that the n times p times 1 minus p is greater than 10. Those are not options for a hypothesis test for variance or standard deviation. You just have to know that it's normal, period. No greater than 30, no n times p times 1 minus p greater than 10, none of that. You have to be given that it's normal. So it has to be given or in a graph, right? Can come from either one of those things. Now, once we have those 2 conditions met, we have to create hypotheses and test them just like we do for any other hypothesis test. Now in here, I actually put both types of hypotheses because a test for a variance and a test for standard deviation are the exact same thing. The only difference is that standard deviation is just plain sigma, whereas variance is sigma squared. So if it's a variance problem, use the squared ones. If it's a standard deviation one, use the sigma ones. Or technically you could write both of them, I suppose, right? It doesn't really matter because they are one and the same, right? All the standard deviation is the square root of the variance. So we have our alpha, which is our level of significance. We're going to find our test statistic right there, which is chi 0 squared. I know it looks like an x, but it's chi, C-H-I, chi. And then we're going to either do the classical approach or the p-value approach. Now, the interesting thing about it is that the calculator does not do either one of these methods. You're going to be stuck doing all of this by hand or using computer output that's given to you. So you're going to have to use the chi-square table to find your test statistic, or excuse me, your critical values, or you're going to need to use your computer output and kind of figure out where everything falls. The weird one is a two-tailed test. The chi 0 squared will fall either on the left or the right. We'll talk more about that one in a later example. And then we're going to make our decisions just like we have for every other kind of test, either reject or not reject based on the critical value placement with the test statistic or because the p-value is low. Gotta love the p-value method. So simple. Is the p-value low? If so, you reject. All right, so let's do a problem here. Oops, I have to go back to the notes right here. There they are. So we're going to do a problem, this problem right here. So we have the graduate record examination, the GRE, is a test required for admission to many U.S. graduate schools. For example, I myself took it when I went off to graduate school at Michigan State University. As a matter of fact, same university I went to for my undergraduate, but I had to take the exam first. So student scores on the verbal reasoning portion are said to have a population standard deviation of 120 by the company that makes this test. You don't believe them, and you believe the value is lower than they claim. So you collect a random sample of 10 scores, and their values are shown below. So here are the values right there. And we have this lovely normal probability plot. So the first thing we need to determine is, are the requirements for conducting a hypothesis test satisfied? Well, if I scroll back up to the requirements, we can remind ourselves that there's only 2 of them, which is kind of nice. You have to have that it's a random sample, and then you have to have that it's normally distributed. But we have both of those things because it says in the problem right here that it is random, right? It's a random sample. And then it's normally distributed because the probability plot shows us that. We loved that section of chapter 7 and we can still love it, right? It's very easy to look at. You can see all the dots are following that central line. No dots, no points are outside of those boundary lines. And there we have it. So we are given in the problem setup that the sample is sample is random, and we can see from the graph that the distribution of the data set is normal because the points all fall in the boundary lines. There we go. All right, now what is the sample standard deviation and its symbol? Well, if you look up here, you can see that I left it in there. I don't actually have to leave it in this graph. I can take it out, but I left it there. But let's remind ourselves how to find these. You would take your calculator, go to Stat, go to Edit, and then you would type in your data, which actually is this data, so I don't need to retype it. I've already typed it in there. Lovely. Then you go to Stat, Calculate, number 1, one variable statistics. My data is in L1, so I'll use L1. Leave the frequency list blank. The only time we use those is section 6.1 for expected value and section 3.3 for weighted means, or means of frequency distributions. So I'm going to go down to Calculate and press Enter. And there it is, 459.3 is the mean, and you look down further and you can see the standard deviation is 105.44619. And then of course the symbol for that, says it right in the calculator, is S, because this is a sample standard deviation. The sample size is 10. We learned about all of these values, well, the first or second week of class, second week, right? Chapter 3 is when we learned about S being the standard deviation symbol and N being the sample size symbol. All right, now, what is the statistical name for S squared and sigma naught squared? So when you look at the test statistic, it's quite a handful. You can see that numerator has an S squared in it, and that denominator has a sigma naught squared. Well, S is the sample standard deviation, so S squared is the sample variance. Remember, because when you take your standard deviation and you square it, you have variance. All right, now what about the sigma naught squared? Well, sigma squared is your population standard deviation, it's population variance. Remember, sigma is population standard deviation, so sigma squared is population variance. But the 0 in it, that naught in the bottom, that subscript, that tells us it's the assumed value from the null hypothesis. So this is our assumed population variance from H0. So that was just a little quick reminder of those things, because when we go to do the test, I want you to have a clue of what the symbols are meaning. As a matter of fact, I'm going to add in here from H0. There. All right. So is there sufficient evidence to conclude that the standard deviation is lower than 120 like the person claimed? Well, all right, our first mission in life is to create our null and alternative hypotheses. That's step 1. So the key is the word lower than, well, and standard deviation. So once we see standard deviation, we know we're using sigma, and then lower than means we know that it's a left-tailed test, right? Lower than 120. Right there, that's our alternative hypothesis written out in words. So now we just have to write it in symbols. There it is. Standard deviation is equal to 120 is what we assume, because that's what the company claimed, and then lower than 120 is what this researcher is claiming. I just labeled those really quickly with what the company is stating is what you assume to be true, unless you can prove it otherwise. Now, just a little quick note, you could write these with the variance. It wouldn't actually change the problem at all. All that would happen is you would write 120 squared. Which turns out to be 14,400. So I get that from taking 120 and squaring it. And there we have it. So that's step 1. Now step 2 is everybody's favorite step. It's given to us right here. Alpha is 0.05. So that makes things nice and easy. Now step 3 is where the hard work comes in. We need to be able to find the test statistic, which is the chi0 squared value, which is this formula right here. So I need to be able to find that. Well, we've already found a whole bunch of it. We found that n was, make this bigger so you can see it. All right, n was 10, so that's 10 take away 1. Then we found that s was 105.446, and we want to square that. And then sigma naught is 120, and then square that, which we actually just found a second ago with the calculator. It's 14,400. Okay. So what I can do is I can make the calculator find the parts of this. So I want 9 times 105.446 squared. That'll be my numerator. And that's that number. And I already know the denominator because I can see it right above me. It's 14400. So I'm going to take my last answer, that 10069 and so on, 100,069. I want to divide it by 14,400. And I get 6.949. And there I just type that in. All right, so that's our test statistic. Done. It's not actually a hard test statistic to find, so it's I guess okay that the calculator doesn't do it for us because it's not going to. Now that we have our test statistic in step 3, we want to be able to find our critical value. So if we look at the method here, it says we have to determine the critical chi-square value using the chi-square table with degrees of freedom n-1. Now keep in mind we're doing a left-tailed test here, so we're going to have to shade and label that left tail bit over there, but it's 1 minus alpha that we actually want for our critical value. That'll make sense in just a minute. Okay, so I start off with degrees of freedom. Degrees of freedom is 10 take away 1, which is 9. So that would be the row that I'm going to go to for my chi-square table. All right, now I need to think about my alpha. So alpha was 0.05. That's the area in the left tail by definition. It's your level of significance because this is a left-tailed test. But if you look at the table for the chi-square values, let me scroll back up to them. There they are. We're doing this test right here, the middle one, right, the left-tailed test. But this table's full of area to the right. So we need to look at the right area. But remember, the entire curve makes 1. So if you take your alpha, which is 0.05, and take it away from 1, you'll get 0.95. It's that pesky complement rule that we learned way back in chapter 5. And that will be the column that we'll actually go to on the chi-square table. So we want the 9th row and we want column 0.95. So let me go back to the chi-square table, scroll up. There's the row 9, there's the 0.95 column, and so our critical value is 3.325. Now remember, I drew this line down here. This actually wasn't originally in that table, but I put it in there because all the values over here on the left side are left-tailed items. So if you have a left-tailed test, you're going to be picking one of the ones from these first 5 columns. If you have a right-tailed test, it'll be over here on the right side. Those are the right-tailed tests. And then two-tailed tests and or confidence intervals will actually be both, right? So for two-tailed tests, you'll have to pick one on one side and one on the other, just like we did in chapter 9. Okay, so it's 3.325. So that's what I drew right here. So I drew a picture, and you have to label this picture. You have to put the chi-square value. Say that it's 3.325. Technically, you don't need to label it on the picture if you don't want to, as long as it's written somewhere that it's equal to 3.325. The actual official labeling for this would be 0.95 comma 9, because it's 1 minus alpha, which is 0.95, and 9 for degrees of freedom. But if you don't want to, you'd have to. You can just say chi-squared 1 minus alpha at this stage in the game. That's fine. All right, so now we have to look at our statistic here, test statistic 6.949, and we have to determine if it is in that shaded region, the critical region is what that's called, or the rejection region, depending on the textbook you're using. And 6.949 is not in there. 6.949, let me draw it for you, is somewhere in here. Right? That's 6.949, which is nowhere close to where we want. So we are going to not reject the null hypothesis. So I just typed that up, right? Because our chi-square value, chi0 squared, our test statistic, is not less than our critical value, we are going to not reject the null hypothesis. And why did I write it like that? Well, let me go back here to step 5 of the classical method. And you can see it says reject your null hypothesis on a left-tailed test, which this is, if your chi0 squared is less than your chi 1 minus alpha squared. And that is not what we have going on, right? Our chi0 squared is not there. In other words, our chi0 squared is not in the rejection region. There. In other words, chi0 squared equals 6.949 is not in the critical region because it's not less than the critical value of chi-squared, which is approximately 3.325. Now, if you want to write all that out, you can, but that's what this says, right? This is mathematical notation for what this is saying. And it just occurred to me, I should be clearer, all of these are approximations because everything we're finding is a rounded decimal. So it's not a big deal if you just write equals, but just keep in mind it actually is approximate because even the table is rounded values. There's more decimal places. The table only shows us a few decimal places. All right, now realize if we don't reject the null hypothesis, that means that we have to say there is not enough evidence to support the claim that the GRE of verbal scores is less than 120. And that's what we'd have to write for step 6. Always remember when you do not reject the null hypothesis, there is not enough evidence. Those two words go hand in hand, right? And then the rest of it is just explaining what your alternative hypothesis was in words, the standard deviation of GRE verbal scores. And before I leave this example behind, I just wanted to really quickly note that this line right here is the test statistic, which is 6.949. All right,